All right, you're back. And you need to check your answers. You need to see if you've answered these questions the right way. Did you learn anything from these horrible NMR videos? That's the last thing that I want to do, maybe on a weekend evening or weekend night, last minute, maybe a couple of hours before the lecture assignments are due, and I'm trying to cram all of this in NMR and all into one video. Oh, my life is miserable. Well, keep in mind, I've had to record all of these. All right, so here we get this example problem. This is where we left it. And I said, can you go through and talk about how we can separate these four compounds from each other based on what we're seeing in the NMR spectra? So I did a lot of the work for you as far as setting up the actual different four molecules or compounds that they have mentioned in the example problem. And this is what we've got to work with. So we need to go through and we need to ding dong the molecule to see how many maybe major signals that we're going to get first. All right, so here we go with our first example. I see hydrogen, hydrogen, hydrogens on all of these carbons. So this particular carbon, ding dong, I'm going to see a signal. That one's different. Ding dong, I'm going to see a signal. And this one, ding dong, I'm going to see a signal. So for this one, there's actually 3 signals in total. All right, so that's the first step. Now, I'm just going to do that with each one of these, all right? So this particular carbon in the second one, we've got a carbon with a bromine directly to the right, and then next door is a carbon with a bromine kind of in the middle. So I'm going to ding dong that one, and then here we get this carbon in the middle, and this is different than the other one, right? We are further away from that bromine on the end. These two things are the same, right? I've got carbon and a bromine on it directly attached. And then here I've got a carbon with a bromine on it directly attached. So in that regard, they are the same. But on the other side of this first carbon had a CBr. And then this particular second carbon doesn't have a CBr attached. It does on one side, but on the other side, it's got that carbon. And this first one did not have just a CH3 group, right? So this is another ding dong, and that's another ding dong. So we're going to see 3 signals with this one as well. All right, so our third example that we've drawn, here we're going to take a look at the ding-dong of the molecules, and it looks like a carbon directly attached to a bromine. That does have some hydrogens. I didn't draw them. We got lazy about it, right? So ding-dong, we're going to see it there. And then this carbon in the middle, that does have hydrogens as well. It does not have bromine directly attached to it, so because of that, that carbon's different, what makes those protons different. So ding-dong, we're going to see one there. And then finally, this one to the left, this is actually identical to the one over on the right. This is a symmetrical molecule. I can basically cut it directly in half and overlap them on top of each other, and they would kind of perfectly match up. So there is a plane of symmetry in this molecule. So the first one to the left is actually equivalent to the very first one that we identified, which was that carbon on the right-hand side. So there's only 2 ding-dongs here, and that means that this is going to be 2 signals in total, and that is it. So automatically, that in itself sets that one so far apart from the other 2 that we've done, okay? And then finally, up here at the top, this was our 4th one, and we need to talk about the number of chemical signals that we would get from here. So if I look at this 3-carbon chain, I'm missing some hydrogens. I'm just going to go ahead and draw them, so that way each carbon has a total of 4 bonds. And then this one here in the center, that one doesn't have any of them at all, right? There's 2 bromines on that one. There's not enough space for another hydrogen, so this one actually does not carry any protons, period. So what we're going to have here in this example is a ding dong right there to the left, because that's a CH3 group. But then another plane of symmetry happens in this molecule. I can fold this in half, and then I can kind of lay them on top of each other, and the left-hand side will perfectly match up with the right-hand side. So the carbon CH3 group over on the right-hand side, that is an identical match to the one on the left-hand side. So this would only give me 1 signal, and that is it. 1 signal, and that makes it yet more different than the previous example, which makes it more different than the 2 examples that we did in the beginning. All right, so we're getting closer. We're answering the problem little bit by little bit. So this one will show me one signal in the NMR. This third option will show me two signals in the NMR. And now the difference that we're going to have to do is in between these, because both of these gave me three signals apiece. So this is where we've got to start looking at splitting in order to see if splitting would actually make a determination on which one actually matches with which NMR the best. So just to kind of save some headache here, we're just going to go ahead and erase these two structures because I've already determined how these are going to be different. I don't need to talk about splitting. I mean, I could go into splitting with those, but why? It doesn't make any difference at all. They are already completely different just based on the number of shifts that I've got. So now I want to go into more detail with each one of these because both of these have three shifts. All right, so let's take a look at example A. And with this example A, I'm going to start with the right-handed carbon first. And this particular carbon, and I'm just going to kind of draw arrows to each of those because we're going to have to identify them. So might as well get it prepped. So with this particular carbon, I only have one neighbor. That one neighbor has two mean kids and an angry parent. So 2 plus 1 is 3. So that means that this is going to be a triplet for me. All right, next I'll do the one on the other end because that's going to be a simpler one as well. It only has one neighbor, and that's the only thing that I have to worry about. So the one here to the left-hand side, I go next door and I say, how many kids you got? And they're going to say 2. And then the person that answers the door is going to be mean and mad and angry. So 2 plus 1 is 3. So that is another triplet that we've got. So I've got 2 triplets at least. And then in the middle, what I have here is, and you've got 3 kids. Oh, goodness gracious. And then next door, you've got 1 kid. So these are different signals, and I treat them differently. I've got to treat them separate. So this is going to be a 3 plus 1, which is a 4. And then next door here, this is a 1 plus 1, and that's a 2. So then I need to multiply them because we're talking about the multiplicity of them. So 4 times 2 is 8. So this is going to be a multiplet. That is how we're going to identify that one. So I've got a multiplet for that middle signal. All right, so then I kind of go on to the second one that we did just a few minutes ago, really. And I'm just going to go ahead and draw the hydrogens on here as well because we're going to need those. So this carbon's got 1 hydrogen in the middle. The one here to the left has got a total of 3. And then here, this carbon needs 2 more. And we'll put them on there just like that. So now we can go through and we can start identifying the multiplicity of these chemical shifts as well. So I'm going to start here on the left-hand side on the end, and I'm going to, and that end one, that middle carbon has 1 proton. So that is a 1 plus 1 is 2. So this is a doublet that we're going to see there. And then on the other end, that's going to be another easy one for me. So on the right-hand side, I go to the middle, and that middle carbon only has 1 proton yet again. So I'll do a 1 plus 1, and that's going to be a 2, and this is going to be a doublet. And then finally, I'll look at the one in the center. And just like before, we said the one to the left and the one to the right are different signals. They're not equivalent to each other. So the way that I work this is that to the left, when I go next door, I'm going to see 3 mean kids and a parent. So that's going to be 3 plus 1 is going to be a 4. And then over on the right-hand side, there's 2 of kids that I don't want that's going to be over there, plus an angry parent that I don't want. So that's going to be a 2 plus 1, which is a 3. And this 4 times 3 is going to be a 12. So this is going to be another multiplet here. So this multiplet will be at least a 4 times 3, which is 12 in theory. And then this particular multiplet, like we said before, was a 4 and then a 2. So 4 times 2 is an 8. But if we just kept it as a multiplet, it would have been enough information to determine the difference. And the reason is because the 2 of these chemical shifts for version A will be triplets. However, in version B, these two signals will be doublets instead. So I see different splitting already. Even if I don't take the multiplet in consideration, they are different splitting techniques that are beginning to happen in these chemical structures. Now, the multiplets, again, if I gave you an actual number, we know they would be different, but very often in a textbook, it would just say multiplet, and they would kind of stop it, and they would leave it for you to figure out. Okay, so that's example problem number 24 answered for you, and hopefully you got something pretty close. Okay, so now let's take a look at this problem. We're kind of working backward here, and these are the ones that I really like because it's ones that you can't really cheat on. So if I'll take a look at problem number 25, it says identify each compound from its molecular formula and its H NMR spectrum, and they give me C9H12. Oh my goodness gracious, C9, 9 carbons. Well, if I look at the NMR signal, what I automatically see here, and this is where my train of thought goes, I see a signal that's going to be here, pretty dominant, and then I see one that's there, and I see one that's there, and I see one that's here, and maybe two of them that's here. So I'm going to put a question mark here, because that could actually be two if I'm not careful. But the reason that I'm circling them is because this is 9 carbon in total. We have carbons and hydrogens on them, and that's pretty much it. So these carbons and hydrogens, I know there can't be 9 different signals, right? Because I'm not seeing those. There's not 9 different carbons in the structure. So that means that maybe we've got a plane of symmetry in here, and that plane of symmetry could come from overlap of a straight chain molecule, or it possibly could come from things like an aromatic ring that would have orthos and metas that are also the same for each other with no kind of crazy functional groups on them, maybe one, and that's about it. So this is kind of where my mind immediately goes to. The number of signals do not match the number of carbons, so we have to have repeats. There's got to be repeats. There have to be equivalents that are going to be here. So when I see these 9 carbons here and these 12 hydrogens, well, look at this. 1, 2, 3, 4, 5, 6, 7, 8, and 9. If I had enough hydrogens that made all of these carbons happy, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There's no way. There's no way, folks. I need 20 hydrogens if all of these carbons are made up like this, all single bonded all the way down. If all of those are there, I need 20 hydrogens, and it's just not going to be there for me. So then you might think, well, you know, there could be like double bonds that are there. There could be triple bonds that are there to take away those hydrogen places. Well, yeah, there is, but now we're getting more and more complicated. I don't want to immediately go to that position. What I want to do, though, is I know that ring systems are pretty common, and I also know that 6 carbons make a pretty stable ring system. So I'm just going to go ahead and start here first. And this is a double, single, double all the way around, and then off of this, there could be something that's hanging off of that ring. And this makes me feel really good because number one, I have all of these double singles that are taking up some hydrogen spots. And then second, it also allows me to have equivalent hydrogens here. If there's just one group off of that ring, I see some orthos that are the same. I see some metas that are the same. And that's kind of what I need in order to make this to match. So what I have left over now is this ring system that took away 6 carbons. So there's 7, there's 8, and there's 9. So maybe, just maybe, I'm getting closer to this structure that possibly makes sense. It might not, but I'm going to check it and I'm going to see if it matches this NMR, and if it does, then great, we got lucky. So now I'm going to go through and write all of the hydrogens that are present here. So that one needs 3, and then this one's 4, and that one's 5, and this one's 6, and that one's 7, and then this one would have 1, there's 8, and then there's 9, and then here's 10, and then there's 11, and then here is 12. So it just so happens that this works out pretty well. Now, I don't know if it matches the NMR, but structure-wise, I mean, this kind of makes sense with us. There's 9 carbons that are there. There's 12 hydrogens that are there. That ring structure of delocalization's pretty stable. I mean, that's very common in these organics. We know that from the lectures of benzenes and substituted benzenes. So I'm going to go through now and just see if this actually makes sense or not. So now I have the NMR in front of me, and with the NMR, I need to go through and I need to see if we've got splitting, and if so, how much splitting. And then I need to ding dong a molecule to see if I'm getting the appropriate number of signals. All right, so here is a CH3 group. Ding dong, I'm going to see a signal here. This CH2 group's different, so ding dong, I'm going to see one there. And then this CH2 group is also different because that's 1 away from the ring. That one was 2 away from the ring, and this CH3 was 3 away from the ring. So ding dong, I'm going to see one there. This particular carbon here in the ring, there's no hydrogen here, so I don't have to worry about ding-donging that one at all. So then I go to either top left or bottom left. Doesn't really matter. It's the same equivalent carbon and the same equivalent protons here. They're both ortho to that propyl group that's on that benzene ring. So ding dong, that one. And then the next one is going to be the meta position. And then if I take a look at the meta position, these are also the same. So they're different than the ortho, but they're one more carbon away from that propyl group. So ding dong, I'm going to see that one there. And then finally, this para position is also going to be a ding dong, and there we go. So this is going to give me 1, 2, 3, 4, 5, 6 ding dong, or chemical shifts. So what we have here is 1, 2, 3. And remember when we did that other benzene, we said they kind of crammed up on top of each other. They're very close together. They're on the same benzene ring. They're slightly different, but they're there. And those 3 kind of all nestled together into, it looked like 2, but it was really 3. And that's kind of probably what we're seeing right there. Now, in addition to that, I also want you to go back and take a look at your reference chart. So let me pull up that reference chart, and right here we see a signal above a 7. So if I go to that reference chart and I look at the delta scale, and that delta scale has 7s that are listed. We had 3 versions of those delta scales, right? So the first one looked like this, and in the 7 ranges, look at this. In the 7 ranges, the 6.5 to 8, what we typically see here is a benzene ring with a proton on it, at least one. So this makes me feel really good about that ring system again, right? And then we had this type of chart as well. And if we're looking here at 7s, well, it looks like, hey, 6.5 to 8, it's a benzene ring with a hydrogen off of it. So that's a possibility. Yeah, we could have an OH group, but it didn't tell me there was an oxygen present. Yeah, we could have an NH2 group, but it didn't tell me there was a nitrogen present. It just said carbons and hydrogens, and that was it. And then if you like this chart better, it's the same thing. We see a little bit above a 7, and then here's the 6.5 to 8, and that's a proton. And then anything else, it really just didn't match at all. So this is going to kind of confirm to me that maybe, just maybe, this is a benzene ring, and that little cluster of 2 that would separate out really if we zoomed in for 3 on the benzene ring kind of makes sense. So if we are kind of feeling lucky, let's just place our focus on the other signals that we're seeing and see if we get splitting that matches those other signals. So with this particular one, look, 1.5 to 1.8. That 1.5 to 1.8, that's actually talking about this one right here, okay? So that particular one that we're seeing right there is split in this particular fashion. So this is a 1, 2, 3, 4, 5, 6. It looks like a 6 splitter for me. All right, so that's not a big deal. We'll kind of take a look at this and see if we get something that kind of matches that. And then here's a 2.5 to 2.7. So that 2.5 to 2.7 looks like that's the zoomed in version of this one. So that looks like a triplet to me. So hopefully we'll get a signal that has a triplet in there, some form, some fashion. And then this very first one that they've kind of integrated out or split it out was a 0.8 to 1.1. And that looks like that first big shift right there. And this particular one looks like it also has been split into 3. So that looks like a triplet as well. All right, so we know that, furthest away from the electron groups, that is really the easiest ones to kind of be shielded or not shielded. It's shielded, and it doesn't really attract the magnet that much. It's easier to flip, and that would be the lowest on the delta scale or the more upfilled one. So this one is probably going to be that one, that CH3 molecule. So next door to that is a carbon with 2 hydrogens, and that is a 2 + 1, which is 3. And that kind of makes sense. This is our CH3 group that we are seeing here at the end of that molecule. So this is carbon number 1, and I'll label that one as carbon number 1 up here, or really A. So I'm going to label this one as A. We've been using A, B's, and C's mostly, so that's what we'll do here as well. All right, so that one matches up pretty well, right? Okay, so the next one that I want to do would be kind of the next one in line here, and that's this next furthest one away from all of the electron mess, and that next one is probably that CH2 group right there. All right, so this CH2 group is nestled in between 2 carbons. Each one of these are different, and I have a 2 + 1, which is a 3 on that side, and I have a 3 + 1, which is a 4 on that side. So that's going to be a 4 × 3, which is 12, and that's a multiplet. And then if I look at this particular one, there's multiple different signals here. There's not necessarily 12, we've got 6, but that's a sign that we've got a multiplet. It won't split and give us 12 different signals. Sometimes they do, but sometimes they don't. It's one of those wishy-washy things with NMR, but it's a very good sign that we've got a multiplet that shows up, and I'm getting a multiplet at that particular carbon as well. All right, so the next one in line, which would be a little bit harder to flip, that would be the one closer to that benzene ring. So this is going to be carbon B, and that means that this is carbon B. So carbon C would actually be the third from the end, or the one closest to the benzene ring, and that's probably going to be this one. And if I look at the neighbors, I go left-handed, there's no proton there, and then if I go right-handed, there's 2, and that 2 + 1 is going to be a 3, and sure enough, that is a triplet. So again, it makes me feel really good about what I did. Now this cluster at 7, it's going to be really hard for me to tell that from the NMR view that they give me, right? And the reason is because I can't zoom in. I can't see this really, really close. However, if I wanted to predict splitting here, the next signal with these hydrogens, what I'm seeing with this one is that there's a neighbor to the left, but not to the right. So that neighbor to the left is 1, 1 + 1 is 2. So this would be a doublet that I would see. And I can kind of almost see a doublet that's getting split in here. I can't necessarily tell that easy, but if I zoomed in, I might be able to see it. Or if they give me pictures like these up here, they might be able to show it to me a little bit better. They just didn't. Then the next one to that is the meta position, and these are different. They are non-equivalent, right? And this is a CH, and that's a CH, so that's going to be a 2 and a 2, and 2 × 2 is 4, so this is a quartet. But this quartet's coming from non-equivalent protons, so that means that this is a double of doublets here. So therefore, I would see 4 shifts, or 4 splittings in that shift, and they all would be about the same height. Again, I can't necessarily see that from the view that they give me, but that's one of the things that I could take away here. And then finally, in the para position, I would see the one to the top right and the one to the bottom right. These are equivalent to each other, right? So again, don't get tricked. They are equivalent to each other. So I do not treat them separately. I get one hydrogen from there, which is 1, and another hydrogen from that second position, which is 2. So then I do the 2 plus 1, which would be 3, and that would give me a triplet here. So if I zoomed in maybe on one of those signals a little closer, I would see a split of 3. But based on what I see here, I feel pretty good about the information that's provided and about the very first kind of guess of structure that we did. It matches up pretty well. Finally, the last thing that I want to show you once we end this example problem, they do provide numbers this time. This is something that they really didn't do previously, but they did provide us a little bit of numbers, and it looks like they calculated like an integral trace or some type of ratio for us to let us know kind of what was what. And it just so happens that those numbers basically pretty match what we had, right? So with this very first signal, I see a 3, and we had 3 protons that were there. And then in this second signal, I see a 2, and there were 2 protons that we had here. And then finally, in this third signal, I see another 2, and we also had 2 protons that were there. And then finally, in this benzene ring, it's ortho, meta, para, it kind of all just kind of clustered together. It really didn't fully separate. It looks like it's one signal. It's just split out in a different way. Well, this is a 5 in total based on the integration. And if you count the number of protons on that benzene ring, I see 1, 2, 3, 4, and 5. It also perfectly matches. So this gives me an idea, hey, these numbers are actually matching the protons in this case. Sometimes it doesn't do that, but because they all were completely different signals, they did not ratio or amplify or subtract from each other, we see a very strong correspondence here between that integral number and the benzene structure as far as the number of protons go. So once more, it helps me feel really good about the structure that we've drawn. So I'm just giving you a hint. I really love these types of problems. It makes you use an NMR and use the lecture material. You can't Google these. You can't look these up. I mean, what are you going to do? How are you going to answer these? How are you going to cheat? And you can't. And that's probably one of the reasons that people get so bad grades during this part, just like in mass spectroscopy and infrared. You don't actually learn the information. You learn how to Google the answers. And that does not help you in organic, and it will not help you with NMR as well. So in the next example problem, we're going to look at another one of these, and this is C5H10O, and it says draw the structure of the compound that would produce this NMR signal. So we're going to do the same thing that we did in the previous one, but we've got some different information that goes along here. I want you to pause this, and I want you to try this on your own. So see if you can come up with C5H10O, a structure that would match this NMR, and convince yourself if it's correct or not. And then in the next video, we'll pick up from this and we'll answer that question at that point.